Hello everyone, I'm Tony from Intel. Today I will give a talk on runtime estimation of application memory latency for performance analysis and optimization. This is the joint work with Huanxin Shen. Here is the outline of my talk. First, I will briefly introduce the background that memory latency is an important but complex factor impacting application performance. Next, I will propose the method of runtime estimation of memory latency at the application level. After that, I will demonstrate how this estimation can be applied to mitigate memory access interference in workload collocation. Finally, I will give the concluding remarks. While memory latency is not a new topic for application performance tuning, today it becomes even more important. For example, modern data analytics and machine learning workloads rely on larger data sets and therefore use more memory. The increasing core number on a server provokes more applications collocated together, exposing mounting pressure to the memory subsystem. For those end-user-facing services, the service level agreement is a rigid objective to sustain, making the impact to application performance an even more important topic. On the other hand, application memory latency during runtime is impacted by many factors. For example, the hardware configurations such as memory interleaving and cache prefetching change the memory access pattern and consequently impacts the latency. With today's NUMA design, given multiple processor nodes in combination with their different CPU scheduling mechanism, memory access may be remote or local with varying latency. By incorporating the large capacity of persistent memory, the access can become more slow. In cases with workload collocated together, memory controllers processing requests from multiple applications, also increasing the waiting time in accesses. In summary, the impact to performance from memory latency is important, but impact can be very complex. Before introducing the estimation method, we first briefly review the background of the cache memory subsystem. The cache memory subsystem is organized in a hierarchical architecture. Each core has its dedicated level 1 and level 2 caches. Those cores in a processor share the last level cache and the memory controllers. When an application needs to access its data, the request is initiated from a core. If the request cannot be served by the dedicated level 1 and level 2 caches, in Intel CPUs, it will wait in a superqueue for further serving. A request in the superqueue is checked in the last level cache. A miss request is masked as ARC miss in the superqueue. It will then be served by the memory, or occasionally, with luck, the cached content in another processor node. In the NUMA architecture, the request may even go to a controller in a remote processor. The idea in the proposed estimation method is to break down the memory latency into cache operation time and memory access time. To estimate the memory access time, we count the cycles that a request waits to be served in the superqueue. Such an idea is supported by the mechanism that any requests with ARC misses are labeled in the superqueue. Platform performance counters at the core level are also available to support such a calculation. A counter provides the total number of unique requests with ARC misses. Another counter gets incremented in each cycle with the number of those requests wait in the superqueue. Combining the two counters, we are able to calculate the average cycles. In summary, our solution estimates the average memory access latency using performance counters. Now we present the breakdown calculation in detail. We estimate the average memory latency as follows. The denominator here is the average frequency. The numerator contains two terms. The first term is the average cycles spent in cache operation. For a specific processor type, we approximate the term with a constant. The second term gives the average cycles spent in memory access. It requires further estimation. We first show how to calculate the average frequency. To do so, we refer to the basic counter that counts the cycles that the cores are unhalted. We also refer to the unhalted reference cycles that gets incremented with respect to the base frequency. Then multiplying the fraction with the base frequency, we know the operating frequency. To calculate the average cycles spent in memory access, we divide the cumulative cycles that the requests with LLCC MEMSYS wait before getting fulfilled with the number of unique requests with LLC MEMSYS. There are 4 counters used in the estimation. Since all of them are core counters, we are able to attribute the estimation to the time period that threads of an application are scheduled to run on those cores. In this way, the memory latency estimated is at the level of that application. To evaluate how well the estimation performs, we look into several different scenarios. In the first scenario, we try to estimate the local memory access latency without explicit background memory load. In the second scenario, we try to estimate the remote memory access latency without explicit background memory load. The third estimation then targets at the latency in accessing the obtained persistent memory. The fourth scenario is about the local memory access latency when there are heavy memory activities loaded in the background. The last scenario follows the fourth one, but the background load is now throttled with memory bandwidth allocation, a hardware feature in CPU. For the ground truth of the latency in different scenarios, we refer to the measurement of the tool, memory latency checker. Memory latency checker, abbreviated as MLC, has a carefully designed measurement thread. The thread traverses an array of data pointers sequentially and calculates the average read latency for reporting. However, it is worth noticing that the tool cannot be used to monitor the latency of another application. We also use an alternative estimation as the baseline for comparison based on Intel Performance Monitoring Guide. This baseline estimates the memory latency by monitoring the counters at the memory controller level. Here we show the experimental results. As we can see here, our estimation is close to the ground truth reported by MLC in the 5 scenarios. The alternative estimation, however, is not. There are multiple reasons. First, the alternative estimation looks at the memory controller level. At this level, it counts all the requests from different applications, but not a target application and estimation. Second, it may miss some important latency. For example, the time spent in traversing the interconnect in remote memory access. In summary, the proposed estimation performs well and much better than the alternative in those scenarios. Next, we demonstrate how the runtime estimation of memory latency at the application level can be applied. The estimation can be used in runtime performance diagnosis to dissect a performance problem in the memory subsystem. Here we have an example about SPECjbb benchmark. When we change the setting of workload CPU binding, the remote memory accesses get impacted. The performance then gets changed. We will not discuss the example in this talk. but recommend the audience to refer to the paper for details. In this talk, we focus on an example of applying the estimation method in runtime performance optimization. Specifically, we show how it can be used to mitigate memory access interference in workload collocation. Workload collocation is a common paradigm to improve cluster utilization. A typical example is in data centers and user-facing workloads are hosted. Those workloads are latency critical. The workload intensity also varies from time to time. When a latency critical workload is not busy, its intensity is low. We then collocate a best effort job to utilize the spare CPU cycles. The best effort job is less performance sensitive and can be throttled on demand. In workload collocation, while the high-level resources such as CPU and memory occupancy are well managed with mature mechanisms, the interferences at the microarchitectural level, such as LLC and memory accesses, are not well managed. Our goal here is to pinpoint and mitigate memory access interference. In this paper, we isolate the memory access interference from a best effort job by throttling its CPU quota. We assume that we do not refer to the application performance information in the process. This is because that application performance information may not be available for various workloads. Even if the information is available, it may not be at the small granularity suitable for timely mitigation. Our solution has two different phases. For a latency critical job, in the first phase, we need to identify the worst case memory latency without memory access interference. The worst case latency is then regarded as a threshold to defend against. To obtain a clean environment during online running in this phase, we fully throttle the BE job by setting its CPU quota to 0. We then wait for periods where the latency critical workload is in high workload intensity. The memory latency of the workload is estimated during these periods. The estimation is finally taken as the threshold. In the second phase, we allow the best effort job to run by identifying and mitigating memory access interference. During running, we repeatedly check the runtime memory latency of the latency critical workload against the threshold. If the runtime latency is not higher than the threshold, we slowly increase the CPU quota of the best effort job by a half core in each step until the quota reaches the maximum quota allowed by the current utilization of the latency critical workload. If the runtime latency is higher than the threshold, we reset the CPU quota to 0. To evaluate the solution, we design an experiment. Here we take Facebook's deep learning recommendation model, abbreviated as DLRM, as the latency critical workload. It is run in inference mode as a recommendation system to provide personalized content based on users' input. Here, the service level objective is defined as an average latency of 9 milliseconds. This is because that when we run the workload in an assumed peak intensity of 24 workers, the average latency is a little bit below 9 milliseconds. We use two different best effort jobs using a well-designed stress tool, stress-ng. In the first scenario of the two scenarios, we let the tool to iterate over different CPU stress tests. In this scenario, the best effort job is a compute-intensive one, but has almost no memory access interference to DLRM. In the second scenario, we let the tool to run the memory bandwidth stress mode. The job then becomes a memory-intensive one with interference to DLRM in memory accesses. In both scenarios, stress-ng is run with 6 workers. When DLRM is running at a lower intensity with 9 workers, we collocate the stress-ng on the server. The workloads are pinned on different hardware threads for well management of CPU cycles. 2 metrics are considered in the evaluation. For the latency critical workload DLRM, we check the average latency to see whether the service level objective is sustained. For the best effort job stress-ng, we check its throughput measured in bulk ops. We use 2 different baselines for comparison. In the first baseline, we use a naive static quota of 1 core for stress-ng. In the second baseline, we do not enforce further quota limit on stress-ng, except for letting it fully utilize the 6 hardware threads with 6 workers. Here we show the experimental results. On the left side, we check whether the service level objective of DLRM is sustained or not. On the right side, we show the throughput of stress-ng. We can see that without further quota limit, the service level objective cannot be maintained in the memory-intensive scenario during memory access interference. On the other hand, with the static quota limit, the throughput of stress-ng is too low in the compute-intensive scenario, even if there is no memory access interference. Our solution is able to mitigate the memory access interference, but at the same time allow best effort jobs to thrive. The experiment demonstrates that this solution performs well. To conclude, we have proposed a new method to calculate runtime memory latency of an application. The method uses performance counters and provides accurate estimation. The runtime estimation of memory latency can be applied to runtime performance diagnosis and optimization. We demonstrate an example of identifying and mitigating memory access interference in workload collocation of DLRM versus stress-ng. It shows that the solution based on the estimation is able to sustain the service level objective of the latency critical workload, but at the same time allow the best effort job to thrive. Here is the end of my talk. Any questions or comments are welcome. Thank you.